A cup of coffee cools on a table, steam rising and thinning into nothing, and no one has ever seen that steam gather itself back, sink down, and return warmth to the cup. This small, ordinary moment holds one of the deepest mysteries physics has ever tried to name. The universe, it seems, remembers only one direction, carrying everything, light, thought, the drift of galaxies, along a current that never reverses, never pauses, never offers a way back. Somewhere in the arrangement of atoms and the strange mathematics of entropy, there is an arrow, invisible but absolute, pointing always toward what comes next. If these quiet explorations have become part of how the night unfolds, staying subscribed means more will arrive in time. For now, the question waits in the stillness. Why does time move forward, and only forward? And the answer begins here. There is a cup of tea sitting on a table somewhere in the world at this very moment, and the tea is growing cold. This is happening with such reliability, with such quiet certainty, that no one watching would think to call it remarkable. The steam rises and disperses into the air above. The warmth seeps through the ceramic walls of the cup and radiates gently into the room, and molecule by molecule, the tea surrenders its heat to everything around it. No one has ever witnessed the reverse of this, not once in all of human history. Not a single observer has seen a cup of cold tea spontaneously draw warmth from the cool air of a kitchen and begin to steam again without any intervention. We accept this without question. We build our kitchens and our lives and our civilizations around the certainty that heat flows from hot things to cold things, that tea cools, that ice in a glass of water will melt on a summer afternoon, that the future is distinguishable from the past, and somewhere else, perhaps in the same house, a block of ice is melting in a bowl. The crystalline structure that held the water molecules in their rigid lattice is coming apart, bond by bond, and liquid water is pooling beneath the diminishing cube. This too has never been observed to happen in reverse under ordinary circumstances. Water at room temperature does not spontaneously gather itself into a frozen block while the surrounding air grows warmer. The scattered molecules do not reassemble themselves into that orderly geometric prison. It simply does not occur. And we know this so deeply that we do not even think to be amazed by the knowing. Consider too the formation of memories, those fragile electrochemical patterns in the tissues of your brain. You remember yesterday. You remember this morning. You may remember a moment from childhood with startling clarity, the quality of light through a window, or the sound of a particular voice. But you do not remember tomorrow. You cannot recall what you will have for breakfast in 3 days, or what words a friend will speak to you next week. Memory reaches only into the past, creating a record of what has happened, but remaining utterly silent about what is yet to come. This asymmetry is so fundamental to the experience of being conscious that we rarely pause to wonder why it should be so. The past is fixed and knowable through the traces it leaves behind. The future is open and uncertain and accessible only through prediction, never through recollection. These everyday miracles, the cooling of tea and the melting of ice and the backward reach of memory, are all manifestations of something profound, something that troubled one particular scientist so deeply that it would shape his entire life and ultimately contribute to the circumstances of his death. Ludwig Boltzmann was born in Vienna in 1844, and by the 1870s he had become consumed by a question that might seem almost childish in its simplicity, but revealed itself to be extraordinarily difficult upon examination. The question was this: why does time have a direction? Why does the universe seem to flow always from past to future, from order to disorder, from hot tea to cold tea? and never the other way around. Boltzmann was a large man, bearded and intense, prone to periods of deep melancholy that alternated with bursts of energetic work. He taught at the University of Vienna and later at Graz and Munich, moving between appointments as personal and professional difficulties followed him. His colleagues considered him brilliant but difficult, and his ideas about the statistical nature of heat and entropy met with considerable resistance from other physicists who found his methods too radical, too dependent on probability and the behavior of countless invisible particles. What Boltzmann understood, and what he spent decades trying to convince others to accept, was that the direction of time is intimately connected to the behavior of enormous numbers of particles. A cup of hot tea contains something like 10 to the 25th power molecules, an almost inconceivable quantity. And these molecules are moving constantly, vibrating and colliding and exchanging energy with one another in patterns of unimaginable complexity. Boltzmann saw that the flow of heat from hot to cold was not a fundamental law written into the fabric of reality, but rather a statistical tendency, an overwhelming probability that emerged from the random motions of countless particles. There are vastly more ways for energy to be spread out evenly than for it to be concentrated in one place, and so systems naturally evolve toward those more probable configurations. The tea cools because there are astronomically more arrangements of molecules in which the tea and the surrounding air share their energy than arrangements in which the tea hoards its heat. This was entropy, the measure of disorder, the quantity that Boltzmann connected to probability and the counting of microscopic states. And entropy, he argued, was the key to understanding why time seems to flow in one direction. The universe moves from less probable configurations to more probable ones, from ordered states to disordered states, from hot tea to lukewarm tea to cold tea. But this explanation, elegant as it was, opened up troubling questions that Boltzmann struggled with for the rest of his life. If the direction of time was merely statistical, merely a matter of overwhelming probability, then it was not truly forbidden for entropy to decrease, for tea to spontaneously reheat, for ice to form from warm water. It was merely extraordinarily unlikely, so unlikely that we would never expect to observe it in the lifetime of the universe. But the laws of physics themselves did not prohibit it. Boltzmann died in 1906, taking his own life while on holiday with his family near Trieste. The reasons were complex, involving chronic health problems and persistent depression, and the exhaustion of decades spent defending his ideas against criticism. But there is something unbearably poignant in the fact that he died still uncertain whether his life's work would be accepted, still defending the statistical interpretation of entropy that is now universally recognized as one of the great insights of 19th century physics. 21 years later, in 1927, the British astronomer and physicist Arthur Eddington was delivering a series of lectures at the University of Cambridge. These lectures would be published the following year as a book called The Nature of the Physical World, and in them, Eddington gave a name to the phenomenon that had so preoccupied Boltzmann. He called it the arrow of time. The phrase was apt, conjuring an image of something that points inexorably in one direction, that distinguishes forward from backward in a way that mere duration does not. A line can be traversed in either direction. An arrow cannot. And Eddington understood that this arrow, this directionality of time, was something almost mysterious, something that the fundamental laws of physics did not seem to require. This is the peculiarity that must be grasped if one is to understand just how strange the arrow of time really is. The equations that describe the behavior of the physical world at its most basic level do not distinguish between past and future. Consider Newton's laws of motion, those elegant relationships between force and mass and acceleration that have guided our understanding of moving bodies for more than 3 centuries. If you film a perfectly elastic collision between 2 billiard balls and then play the film in reverse, the reverse motion is also a valid solution to Newton's equations. Nothing in the mathematics of Newtonian mechanics would allow you to determine which version of the film was running forward and which was running backward. Both are equally consistent with the laws. The same is true of Maxwell's equations, those 4 beautiful relationships that describe the behavior of electric and magnetic fields and light itself. A beam of light traveling from left to right is described by exactly the same mathematics as a beam of light traveling from right to left. The equations are symmetric under time reversal. They do not care whether time runs forward or backward. And when Albert Einstein formulated his theories of relativity in the early 20th century, special relativity in 1905 and general relativity in 1915, he found the same symmetry. The Einstein field equations that describe how matter curves spacetime and how that curvature guides the motion of matter do not distinguish between past and future. A planet orbiting a star and gradually spiraling inward due to the emission of gravitational waves is described by equations that work equally well for a planet spiraling outward, gathering gravitational wave energy from some external source. The mathematics admits both possibilities with perfect equanimity. This is deeply strange. The fundamental equations of physics are time symmetric, meaning they work just as well when time is reversed, and yet our experience of the world is radically time asymmetric. We remember the past, but not the future. We grow older, but never younger. Eggs break, but never unbreak. Somewhere in the transition from the microscopic world of atoms and fields to the macroscopic world of teacups and memory, something happens that introduces a direction to time. But what? For a long while, physicists believed that the laws of physics were perfectly symmetric in a slightly more technical sense. They believed that if you combined 3 transformations, reversing the direction of time, reversing the spatial coordinates, so that left became right and up became down, and replacing every particle with its antiparticle, the laws of physics would remain unchanged. This combined symmetry is called CPT symmetry, where C stands for charge conjugation, which is the swapping of particles with antiparticles. P stands for parity, which is the mirror reversal of space, and T stands for time reversal. The CPT theorem states that any quantum field theory that satisfies certain basic requirements must be symmetric under the combination of all 3 transformations. But there was still the question of whether each symmetry held individually. Did the laws of physics remain unchanged under time reversal alone, or under the combination of charge conjugation and parity? For many years it was assumed that they did. But in 1964, an experiment at Brookhaven National Laboratory on Long Island revealed something unexpected. James Cronin and Val Fitch, working with their collaborators, were studying the decay of particles called neutral kaons. These particles are unstable, existing for only a tiny fraction of a second before transforming into other particles. And they come in 2 varieties that differ in their behavior under the combined transformation of charge conjugation and parity. One variety decays quickly into 2 particles called pions, while the other variety decays more slowly into 3 pions. If the laws of physics were perfectly symmetric under the combination of charge conjugation and parity, these 2 varieties should remain distinct, never mixing with one another. But Cronin and Fitch discovered that the long-lived variety sometimes decayed into 2 pions instead of 3, a decay that should have been forbidden if CP symmetry were exact. The symmetry was violated, broken by some tiny asymmetry in the underlying physics. The effect was small, occurring in only about 2 out of every 1,000 decays, but it was unmistakable. Cronin and Fitch would later share the Nobel Prize in Physics for this discovery, which demonstrated that the laws of physics are not quite symmetric under the combination of charge conjugation and parity. And because the CPT symmetry is believed to be exact, a violation of CP symmetry implies a violation of time reversal symmetry as well. Somewhere in the quantum fields and particles that make up the universe, there is a subtle preference for one direction of time over the other. But this tiny asymmetry, this slight bias in the decay of obscure, unstable particles, seems far too small and far too remote from everyday experience to explain why tea cools and ice melts and memory reaches only into the past. Here is a haunting detail to consider as you settle deeper into whatever position you have found comfortable. If you were to film a single atom, just one atom isolated in otherwise empty space, oscillating and emitting and absorbing photons according to the laws of quantum mechanics, and if someone were then to show you the film without telling you whether it was running forward or backward, you would not be able to tell. The motion of that single atom would appear equally valid, equally consistent with physical law, in either direction. There would be no clue, no telltale sign, no marker that would allow you to determine which way time was supposed to flow. This is the puzzle that Boltzmann glimpsed and that still haunts physics today. At the level of individual particles and fundamental interactions, time has no obvious direction. The equations run forward and backward with equal facility, and yet the universe we actually inhabit is saturated with directionality, with processes that happen readily in one direction and never in reverse, with causes that precede effects and memories that record the past. Something enormous is happening. Some grand asymmetry is being imposed on a symmetric foundation, and physics at its deepest level does not fully explain how this comes to be. The cooling of your tea, should you have a cup beside you, is a tiny local expression of this cosmic mystery. The heat flows outward, the entropy increases, and the arrow of time points steadily in its accustomed direction. It has always done so, as far as we can tell, since the earliest moments of the universe. And yet the fundamental laws seem indifferent to this direction, as if they are waiting for some deeper explanation that we have not yet found. This is where we begin. With a clock that never runs backward, with tea that cools and ice that melts and memories that form only of what has already happened, with the tragedy of Boltzmann and the insight of Eddington and the patient accumulation of evidence that something is profoundly strange about the way time moves through the universe. The question is not whether time has a direction, for our every experience confirms that it does. The question is why. Let us imagine for a moment that time is not a line, but a river, and that this river flows always in one direction, carrying everything upon its current towards some distant and unknowable sea. We cannot paddle upstream, no matter how we might wish to return to moments already past. We cannot step out of the water and walk back along the bank to yesterday. The river moves, and we move with it, and this movement has a name that was given to it by a quiet German physicist in the middle of the 19th century, a name drawn from the ancient Greek language. A name that sounds almost gentle when you say it slowly, letting each syllable settle like a leaf upon still water. Rudolf Clausius was a careful man, a man who spent his days surrounded by equations and the hiss of steam engines. And in the year 1865, he found himself in need of a new word. The existing vocabulary of physics did not contain what he required. He needed a term for something that had no shape you could hold, no color you could see, no sound you could hear, and yet was present in every process, every change, every transformation of energy from one form to another. He reached back through the centuries to the Greek word trope, meaning transformation or turning. And from this root, he fashioned the word entropy. He chose it deliberately so that it would sound similar to energy, for he sensed that these two concepts were deeply connected, like siblings who resemble one another but are not quite the same. What Clausius had noticed, through years of studying heat and work and the behavior of engines, was that something always seemed to be lost. Not energy itself, for energy is conserved, passing from one form to another, but never truly disappearing. What was lost was something more subtle, something related to the usefulness of that energy, its ability to do work, its organization and concentration. When a hot object is placed beside a cold one, heat flows from the warmer to the cooler until both reach the same temperature. And though the total energy remains unchanged, something has dispersed, something has spread out, something has become less available for any purposeful task. Clausius called this spreading out entropy, and he observed that in any natural process, the total entropy of a closed system tends to increase, or at best remain the same, but never to decrease on its own. 2 years after Clausius gave entropy its name, a Scottish physicist named James Clerk Maxwell sat down to write a letter to a colleague, and in that letter he described a peculiar thought experiment that would trouble physicists for the better part of a century. Maxwell asked his correspondent to imagine a container divided in two by a wall, with a tiny door set into that wall, a door so small that only a single molecule might pass through it at a time. On one side of the door stood a being of exceptional cleverness and patience, a being whom Maxwell's friend later called a demon, though Maxwell himself never used that word. This demon could see individual molecules and could tell the fast ones from the slow ones, for temperature is really just the average speed of molecules, with faster molecules corresponding to higher temperatures and slower molecules to lower ones. The demon's task was simple. Whenever a fast molecule approached the door from the left, the demon would open it and let the molecule pass through to the right. Whenever a slow molecule approached from the right, the demon would open the door and let it pass to the left. All other molecules would find the door firmly closed. If the demon performed this sorting long enough, Maxwell reasoned, eventually all the fast molecules would accumulate on one side and all the slow molecules on the other. One side would become hot and the other cold, even though they had started at the same temperature. Heat would have flowed from cold to hot without any work being done, and the entropy of the system would have decreased. The second law of thermodynamics, which Clausius had so carefully formulated, would be violated, not by any physical process, but by intelligence itself, by the act of knowing and choosing. Maxwell did not believe that such demons actually existed, but he raised the puzzle to illuminate something important about the nature of the second law. It was not, he suspected, an absolute prohibition like the conservation of energy. It was something different, something that emerged not from the behavior of individual particles, but from the collective behavior of unimaginably vast numbers of them. The second law was statistical in character, a statement about what was overwhelmingly likely rather than what was absolutely certain. This insight was developed most fully by Ludwig Boltzmann, an Austrian physicist whose life was marked by brilliance and melancholy in nearly equal measure. Boltzmann understood that the universe contains not just matter and energy, but also arrangements, configurations, ways that particles can be distributed through space and among various states of motion. Some arrangements are highly ordered, like the molecules in a crystal, all lined up in neat rows, or the molecules in your teacup, all moving together in the same direction. Other arrangements are disordered, with molecules pointing every which way, moving at different speeds, distributed seemingly at random. Boltzmann realized that there are vastly almost inconceivably more disordered arrangements than ordered ones. If you take a deck of cards and shuffle it thoroughly, the chance of ending up with all the cards in perfect order, ace through king in each suit, is vanishingly small. Not because there is any law forbidding that arrangement, but simply because there are so many other arrangements that shuffling could produce. The ordered state is possible, but improbable. The disordered states are countless and therefore nearly certain. Entropy, Boltzmann showed, is a measure of this disorder, or more precisely, a measure of the number of microscopic arrangements that correspond to a given macroscopic state. A state of high entropy is one that can be realized in many different ways at the molecular level. A state of low entropy is one that demands a very particular arrangement, a special configuration that admits little variation. The second law of thermodynamics, in Boltzmann's view, simply states that systems tend to evolve towards states that can be realized in more ways, which is to say, toward higher entropy, toward greater disorder, toward the statistically typical. Boltzmann died in 1906 during a holiday in Trieste, and his body was returned to Vienna, where he was buried in the central cemetery among the city's composers and poets and other luminaries. His grave is marked by a stone bust of his likeness, and carved into that stone, above his name and dates, is a single equation, perhaps the most elegant summary of a life's work that any tombstone has ever borne. It reads simply, Ceph equals K log W, where S is entropy. K is a constant that now bears Boltzmann's name, and W is the number of microstates corresponding to a given macrostate. In that spare equation lies the entire statistical understanding of entropy, the recognition that disorder is not a mystical force, but a matter of counting possibilities. Now, here is something remarkable to consider as you settle deeper into your pillow and let your thoughts grow soft around the edges. The second law of thermodynamics, despite its stately name, is not truly a law in the strictest sense. It is a statement about probabilities, about what is so overwhelmingly likely as to be effectively certain in practice, but not logically impossible to violate. Consider a cup of tea that has fallen from a table and shattered upon the floor, spilling its contents across the tiles. The second law tells us that this process, the falling and shattering and spilling, is accompanied by an increase in entropy. The ordered state of the intact cup has given way to the disordered state of fragments and puddles. But could the cup, in principle, spontaneously reassemble? Could all those scattered molecules, through their random motions, happen to converge and flow upward and fuse themselves back into a pristine vessel, rising from the floor to return to the tabletop from which it fell? The laws of physics at the microscopic level do not forbid this. Every collision between molecules is reversible. Every trajectory traced by a fragment could, in theory, be traced backward. There is no fundamental barrier, no cosmic prohibition against the cup reassembling itself. What there is, instead, is probability. If you were to calculate the odds of such a spontaneous reassembly, you would arrive at a number so small that it defeats all ordinary language. It has been estimated that the probability is roughly 1 in 10, raised to the power of 10, raised to the power of 23. This is not merely an astronomical number. It is a number so vast that writing it out in full would require more digits than there are atoms in the observable universe. You could wait for longer than the current age of the cosmos, far longer, inconceivably longer, and still the cup would not reassemble. Not because it cannot, but because the universe is simply not old enough to give such an improbability any realistic chance of occurring. This is the nature of the second law. It does not say that entropy must always increase. It says that entropy almost certainly will increase, and that the almost covers a margin so wide that no observation has ever found it wanting. In all of human history, across all the experiments ever conducted, and all the natural phenomena ever recorded, no one has witnessed a spontaneous decrease in the entropy of a closed system. The tea grows cold. The ice melts. The perfume diffuses through the room. Time flows only downstream. But what of Maxwell's demon? Does the clever being at the tiny door truly violate the second law? This question lingered for decades, passed from one physicist to another, like a puzzle box that no one quite knew how to open. It was finally resolved, or at least clarified, in 1929 by Leo Szilard, a Hungarian physicist who would later play a role in far grimmer matters, but who at that moment was concerned purely with the relationship between information and thermodynamics. Szilard showed that the demon's apparent violation of the second law was an illusion, arising from a failure to account for everything happening in the system. When the demon observes a molecule and determines whether it is fast or slow, the demon acquires information. That information must be stored somewhere, in the demon's memory or in whatever physical substrate serves as the demon's brain. And when that information is eventually erased, as it must be if the demon is to continue operating indefinitely, the erasure generates entropy. The act of forgetting, the clearing of the slate, the resetting of the memory, produces exactly enough entropy to compensate for the decrease that the demon's sorting achieved. The books balance in the end. The second law stands. This connection between information and entropy, first glimpsed by Szilard and later developed by others, suggests something profound about the nature of reality itself. Information is physical. Knowing something, remembering something, measuring something. These are not abstract processes floating above the material world. They are enacted by physical systems, neurons and transistors and molecular bonds, and they carry thermodynamic costs. Even now, as you listen to these words and process their meaning, your brain is creating entropy. The act of thinking generates waste heat, disperses energy, adds its tiny contribution to the slow unwinding of all things. This might sound melancholy, but perhaps it is also strangely comforting. Your thoughts are real in the most fundamental sense. They are written into the physics of the universe, accounted for in its ledger of energy and entropy. Every idea you have, every memory you form, every dream that passes through your sleeping mind, these leave their traces in the thermodynamic history of the cosmos. And yet, for all its explanatory power, entropy raises a deeper question, a question that Boltzmann himself could not fully answer, and that remains alive in physics to this day. If the second law tells us that entropy tends to increase, that systems evolve toward disorder, that the universe is slowly shuffling itself toward a state of maximum randomness, then we must ask how this shuffling began. For the entropy to be increasing now, it must have been lower in the past. And if we trace that past backward, further and further, through the history of the Earth and the Sun and the galaxies, we arrive eventually at the beginning of the universe itself, at the moment of the Big Bang. And there we find something very strange. The early universe, according to all our best theories and observations, was in a state of extraordinarily low entropy. It was not a disordered chaos, but something remarkably smooth and uniform. A configuration that could be realized in relatively few ways, a state far from equilibrium, far from the typical condition that random shuffling would produce. This is the great puzzle, the mystery at the heart of the arrow of time. The second law explains why entropy increases, why the future differs from the past, why we remember yesterday but not tomorrow. But it does not explain why entropy started so low in the first place. The arrow of time points forward because of entropy, but entropy itself seems to require an explanation, a reason for its initial conditions, a story about why the universe began in such an improbable state. This is not a question with a settled answer. It is a question that physicists and philosophers continue to ponder. A question that may be connected to the origin of the universe itself, to the nature of gravity, to the shape of space and time on the largest scales. But that is a matter for another time. And your eyelids have grown heavy, and the river of entropy flows gently on, carrying you toward sleep, toward dreams, toward the quiet hours that stretch before the dawn. The cup will not reassemble. The tea will not grow warm again. But in this river, there is a kind of peace, a naturalness, a belonging. You are part of the current, and the current flows as it must, as it always has, as perhaps it always will. In the autumn of 1964, two radio astronomers named Arno Penzias and Robert Wilson were working with a rather unusual piece of equipment at Bell Telephone Laboratories in Holmdel, New Jersey, a quiet corner of the American Northeast, where the landscape rolls gently toward the Atlantic coast. And where, at that particular time, a horn-shaped antenna, originally designed for satellite communication, was about to reveal something rather profound about the nature of the cosmos, though neither scientist had any inkling of this when they first encountered the problem that would come to define their careers, and which they initially attributed to something far more mundane than the echo of creation itself. The antenna in question was called the Holmdel horn antenna, and it resembled, in its own peculiar way, an enormous ear trumpet pointed toward the heavens, a receiving device that had been built to detect radio signals bounced off the Echo balloon satellite, but which Penzias and Wilson had repurposed for radio astronomy, hoping to measure the intensity of radio waves emanating from our own Milky Way galaxy. A perfectly reasonable scientific endeavor that should have proceeded without any particular drama, except for the presence of a persistent noise that refused to go away, no matter how carefully they calibrated their instruments, or how thoroughly they accounted for every known source of interference. This noise was a faint microwave hiss, uniform and constant, arriving from every direction in the sky with no apparent source, no origin that could be traced to any star or galaxy or terrestrial transmission, and it registered at a temperature of approximately 3 degrees above absolute zero, which is to say 3 Kelvin, a measurement that seemed entirely arbitrary and unexplainable within the context of anything the two scientists knew about radio astronomy at that particular moment in history. They checked their equipment meticulously, as any good experimentalist would, examining every cable and connection, every amplifier and receiver, searching for the source of this unwanted signal that was contaminating what should have been pristine astronomical data. And in the process of this investigation, they discovered that a pair of pigeons had taken up residence inside the horn antenna itself, building a nest and covering the interior surfaces with what Penzias would later describe, in the understated manner of a professional scientist, as a white dielectric material, which is to say, droppings. The pigeons were removed, relocated to a distant location, though they promptly returned, as pigeons are wont to do, and were eventually dealt with more permanently. And the interior of the antenna was cleaned thoroughly, but the noise persisted, undiminished and unexplained, arriving from the cosmos with the same quiet constancy as before, as though the birds had never been there at all, as though the hiss had nothing whatsoever to do with the biological activities of urban wildlife, and everything to do with something far more ancient and far more fundamental. It was only when Penzias happened to mention his frustrations to a colleague, who happened to know of some theoretical work being done at nearby Princeton University, that the pieces began to fall into place. For at Princeton, a group of physicists led by Robert Dicke had been preparing to search for precisely this kind of radiation, the afterglow of the Big Bang itself, a prediction that had been made decades earlier but largely forgotten. And when Dicke learned of the Bell Lab's measurements, he reportedly turned to his colleagues and said, rather quietly, that they had been scooped. What Penzias and Wilson had discovered, quite by accident, and with considerable assistance from the pigeons who had first drawn their attention to the equipment, was the cosmic microwave background radiation, the oldest light in the universe, released approximately 380,000 years after the Big Bang, when the cosmos had cooled sufficiently for electrons and protons to combine into neutral hydrogen atoms, allowing photons to travel freely through space for the first time, no longer scattered by the dense fog of charged particles that had previously filled all of existence. This radiation has been traveling through the expanding universe ever since that moment, stretched by the expansion of space from its original visible wavelengths into the microwave portion of the electromagnetic spectrum, cooling from its initial temperature of several thousand degrees to the frigid 3 Kelvin that Penzias and Wilson measured in their pigeon-haunted antenna, and it fills the entire cosmos uniformly, arriving from every direction with almost perfect isotropy, a fossil record of the universe's earliest visible epoch, preserved in the gentle hiss of radiostatic. For their accidental discovery, Penzias and Wilson would eventually receive the Nobel Prize in Physics in 1978, though one imagines the pigeons received no such recognition for their indirect contribution to the advancement of human knowledge. The cosmic microwave background had been detected, but the instruments available in 1965 were far too crude to reveal its finer details, and for more than 2 decades, scientists could only measure its overall temperature and its remarkable uniformity, knowing that somewhere within this ancient light there must be tiny variations, subtle ripples that would eventually grow into the galaxies and galaxy clusters that populate the universe today, but lacking the technological means to observe them directly. This changed in November of 1989, when the National Aeronautics and Space Administration launched a satellite called the Cosmic Background Explorer, known by its acronym COBE, which carried instruments specifically designed to map the cosmic microwave background with unprecedented precision, observing from above Earth's atmosphere, where terrestrial interference could not contaminate the delicate measurements, and where the instruments could cool to temperatures approaching absolute zero without the complications of operating in a terrestrial environment. The COBE satellite observed the sky for 4 years, slowly building a map of the microwave radiation arriving from every direction, and what it revealed was nothing less than a portrait of the infant universe, an image of the cosmos, as it appeared 380,000 years after the Big Bang, which may sound like an enormous span of time by human standards, but which represents only a tiny fraction of the universe's current age of approximately 13.8 billion years, making this image, in a very real sense, a photograph of the universe when it was still an infant, barely beginning its long journey toward the complex and differentiated cosmos we observe today. The most striking feature of this portrait was its uniformity, the extraordinary smoothness of the early universe. For the temperature variations that COBE detected were astonishingly small, only about 1 part in 100,000, which is to say that if the average temperature was 3 Kelvin, the hottest and coldest regions differed by only about 30 millionths of a degree, a level of uniformity that seems almost impossibly precise, like finding a swimming pool so perfectly still that the difference in water level from one end to the other amounts to less than the width of a human hair. These tiny variations, small as they were, represented the seeds of all cosmic structure. The slightly denser and slightly less dense regions that would eventually, over billions of years of gravitational attraction, collapse into galaxies and stars and planets, and, ultimately, into the atoms that compose your own body and the device upon which these words are rendered. But the variations themselves were so minuscule that their detection required instruments of extraordinary sensitivity, and the fact that the early universe was so smooth, so uniform, so very nearly the same in every direction, was itself a puzzle that would come to dominate cosmological thinking for decades to come. The COBE results were refined and extended by subsequent missions, most notably by the Planck satellite, launched by the European Space Agency in May of 2009, which carried instruments even more sensitive than those aboard COBE, and which observed the cosmic microwave background from its orbit around the second Lagrange point, a gravitationally stable location approximately 1.5 million kilometers from Earth in the direction opposite the Sun, where the satellite could maintain a constant orientation and where thermal interference from Earth and Moon could be minimized. The Planck satellite released its initial findings in 2013, providing the most detailed portrait of the cosmic microwave background ever obtained, with resolution fine enough to detect features corresponding to regions less than 1 degree across on the sky, and confirming with even greater precision the remarkable smoothness of the early universe, while simultaneously mapping the tiny fluctuations that would become the scaffolding upon which all subsequent cosmic structure would be built. What this smoothness represents, when translated into the language of thermodynamics that has occupied our attention throughout this narration, is a state of extraordinarily low entropy, a configuration of matter and energy so highly ordered, so improbable, so far from equilibrium, that its existence demands explanation, and it is here that we encounter one of the most profound and troubling calculations in all of physics, performed by the British mathematician and physicist Roger Penrose, who attempted to quantify just how special the initial conditions of the Big Bang truly were. Penrose's calculation proceeded by comparing the actual initial state of the universe to all the possible states it might have occupied, asking what fraction of possible configurations would have led to a cosmos resembling our own, with its smooth early distribution of matter and its subsequent evolution toward the structured universe we observe today. And the answer he obtained was staggeringly small, expressed as a probability of approximately 1 in 10 raised to the power of 10 raised to the power of 123. This number is so large that it defies ordinary comprehension, for even to write it out in ordinary decimal notation would require more digits than there are particles in the observable universe, more digits than there are possible arrangements of all the atoms in all the stars, in all the galaxies, a number so absurdly improbable that no analogy can do it justice, though we might try by saying that finding the universe in such a state is rather like shuffling an inconceivably vast deck of cards and having them emerge in perfect numerical order by suit, except that even this comparison understates the improbability by countless orders of magnitude. The mystery, then, is not why entropy increases, for we have already seen that this is simply the natural tendency of systems to evolve toward more probable configurations, the statistical inevitability of moving from the rare and special to the common and unremarkable, but rather why the universe began in such an extraordinarily improbable state in the first place, why the initial conditions were so precisely tuned, so remarkably ordered, so preposterously far from equilibrium that the subsequent increase in entropy has been able to continue for nearly 14 billion years without the cosmos reaching its maximum entropy state. Consider the image of a pristine deck of cards found in the aftermath of a hurricane, arranged in perfect numerical order from ace to king in each suit, lying there amid the debris and destruction with every card precisely where it should be. untouched by the chaos that has rearranged everything else into disorder. And you will have some sense of the puzzle that confronts cosmologists when they contemplate the early universe. Though again, the analogy understates the improbability by factors that cannot be meaningfully expressed. The cosmic microwave background, with its exquisite smoothness and its tiny, nearly imperceptible variations, is the evidence of this impossibly ordered beginning. The fingerprint of a universe that started in a state so special that its existence seems to cry out for explanation. And yet no fully satisfactory explanation has been found. No theory that accounts for why the Big Bang produced a cosmos so far from thermal equilibrium, so primed for the long, slow increase in entropy that has characterized its subsequent evolution. Some physicists have proposed inflationary models, in which a brief period of exponential expansion in the universe's earliest moments smoothed out initial irregularities and produced the uniformity we observe. But these models, while explaining the smoothness, do not fully account for the low entropy, for they merely push the puzzle back to earlier times, raising the question of why the universe was in a state capable of undergoing inflation in the first place. Others have speculated about selection effects and the anthropic principle, suggesting that only universes with low entropy beginnings could produce observers capable of asking such questions. But this explanation, while perhaps containing a grain of truth, feels more like an acknowledgement of our ignorance than a genuine solution. A way of saying that the puzzle exists without truly explaining why. And so the mystery remains, the suspicious beginning that haunts all our discussions of time's arrow, for the increase of entropy that defines the direction of time, that separates past from future and memory from anticipation, depends entirely upon this extraordinary initial condition, this preposterously special configuration that emerged from the Big Bang for reasons we do not yet understand, and which may represent the deepest puzzle in all of physics. The question that sits at the very foundation of our understanding of time and change, and the nature of the cosmos itself, waiting patiently for an answer that may or may not ever come. The universe, it turns out, keeps very good records, and if you know how to read them, you can see the passage of time written across the sky in patterns so vast that light itself takes millions upon millions of years simply to cross from one side to the other. And yet these patterns, these great sweeping structures of matter and emptiness, tell a story that runs in only one direction, a story of gathering and accumulation, of things coming together and never quite coming apart again. And it is a story that has been unfolding for nearly 14 billion years now, each chapter building upon the last in a sequence that cannot be reversed, not by any known process, not by any conceivable mechanism within the laws of physics as we understand them. When astronomers first began mapping the positions of galaxies in earnest, they expected to find something rather like a uniform scattering, perhaps with a few clusters here and there, the way you might expect raisins to be distributed through a well-mixed pudding. But what they discovered instead was something far more intricate and far more beautiful. A vast network of filaments and sheets and nodes, with galaxies strung along these structures like dewdrops on a spider's web. And between these filaments lay enormous voids, regions of space, hundreds of millions of light years across, where almost nothing exists at all, just darkness and emptiness and the faintest whisper of hydrogen gas. And this arrangement, this cosmic web as it came to be called, is not a random pattern, but rather the inevitable result of gravity working upon matter over billions of years, pulling things together, amplifying tiny initial differences, turning the nearly uniform soup of the early universe into the lumpy, textured, deeply structured cosmos we observe today at Apache Point Observatory in New Mexico, perched on a ridge in the Sacramento Mountains at an elevation of about 9,000 feet. Astronomers have been conducting one of the most ambitious mapping projects in the history of science, and this project, known as the Sloan Digital Sky Survey, began its systematic observations in the year 2000 and has continued through various phases ever since, cataloguing the positions, distances, brightnesses, and spectral properties of celestial objects with a patience and thoroughness that would make any archivist proud. And over the course of more than 2 decades, the survey has recorded the locations of more than 3 million galaxies, building up a 3-dimensional map of the universe that extends outward for billions of light years in every direction. And when you look at this map, when you see the data rendered as a visualization, with each galaxy represented as a tiny point of light, what emerges is that web-like structure, those filaments and voids, that unmistakable architecture of cosmic time. The patterns revealed by surveys like this one tell us something profound about the nature of time itself, because the structures we see could only have formed in one direction, from smooth to lumpy, from uniform to textured, from simple to complex in this particular gravitational sense, and there is no process by which the cosmic web could spontaneously unknit itself, no mechanism by which the galaxies could spread back out into a uniform distribution, no way for the voids to fill in and the filaments to dissolve. Not without an input of energy and organization so vast as to be effectively impossible, and so the very existence of this structure, the mere fact that we can look up and see galaxies clustered along these great cosmic highways rather than scattered uniformly across the sky, is itself a record of time's passage, a signature written in the positions of a trillion stars. In 2014, an astronomer named Brent Tully, working with his colleagues at the University of Hawaii, published a paper that redefined our understanding of our cosmic address, for they had used careful measurements of galaxy motions and distances to map out the gravitational basin in which our own Milky Way resides, the region of space within which all galaxies are flowing toward a common center of mass. And they found that this basin, this gravitational watershed, was far larger than anyone had previously realized, encompassing some 100,000 galaxies spread across a region more than 500 million light-years in diameter. And Tully gave this structure a name drawn from the Hawaiian language of the islands where he worked, calling it Laniakea, which means immense heaven. And the name seems fitting for something so vast that even traveling at the speed of light, you would need 500 million years to cross from one edge to the other. Laniakea is not merely a collection of galaxies that happen to be near each other in space, but rather a gravitationally bound system in which all the component parts are falling toward a common center, drawn by the combined mass of all that visible matter plus something else, something unseen, something that makes up the greater part of the gravitational attraction but emits no light, and interacts with ordinary matter only through gravity. And this brings us to one of the great mysteries of 20th century astronomy, a mystery first glimpsed by a Swiss astronomer working in California nearly a century ago. Fritz Zwicky was a brilliant and cantankerous figure, a physicist at the California Institute of Technology, who made contributions to fields ranging from supernovae to neutron stars to gravitational lensing. And in 1933, he turned his attention to a cluster of galaxies in the constellation Coma Berenices, a rich gathering of thousands of galaxies bound together by their mutual gravitational attraction. And Zwicky did something quite clever. He measured the velocities of the galaxies within this cluster by examining the Doppler shifts in their light, and he calculated how much mass would be needed to hold the cluster together against these motions, to prevent the galaxies from simply flying apart into space. And when he compared this required mass to the mass, he could actually see the mass contained in all those visible galaxies with their billions of stars. He found a discrepancy that was deeply troubling. For the cluster seem to contain far more gravitational pull than could be accounted for by luminous matter alone. Perhaps 10 times as much, perhaps even more. Zwicky called this missing component Dunkelmaterie, dark matter, and though his contemporaries largely ignored or dismissed his findings, the evidence for this unseen substance has only grown stronger in the decades since, with observations of galaxy rotation curves, of gravitational lensing, of the cosmic microwave background radiation, all pointing toward the same conclusion, that roughly 85% of all the matter in the universe is something we cannot see, something that neither emits nor absorbs light, something that interacts with ordinary matter only through gravity. And yet this dark matter is not merely a passive presence, for it is the scaffolding upon which the cosmic web is built, the gravitational skeleton around which ordinary matter accumulates, and the structures we see in galaxy surveys, like the Sloan Digital Sky Survey, are shaped as much by dark matter as by the luminous galaxies that trace out its distribution. The process by which these structures form is fundamentally irreversible. A one-way transformation from smooth to lumpy that cannot be undone. And nowhere is this irreversibility more apparent than in the formation of stars, those great nuclear furnaces that convert hydrogen into helium and helium into heavier elements, releasing energy in the process and bathing their surroundings in light. For a star forms when a cloud of gas collapses under its own gravity, falling inward upon itself until the pressure and temperature at the center become high enough to ignite nuclear fusion. And once this collapse has occurred, once the star has formed, there is no going back. No process by which the star can spontaneously expand back into a diffuse cloud. No mechanism by which the fusion products can separate back into their original components without an enormous input of energy. And so every star in the sky is a record of a gravitational collapse that happened once and cannot be reversed. A permanent marker of time's passage written in nuclear fire. And when stars die, when they exhaust their nuclear fuel and can no longer generate the outward pressure needed to resist gravity's inward pull, they may undergo even more dramatic collapses. And for the most massive stars, the final collapse is so complete, so total, that nothing can halt it. Not the pressure of electrons, not the pressure of neutrons, nothing. And the result is a black hole. A region of space where gravity has become so strong that not even light can escape. A one-way boundary from which nothing returns. And black holes are, in a very precise sense, the ultimate expression of time's arrow, the final end state toward which gravitating systems tend, the maximum possible concentration of mass and the maximum possible entropy for a given size. In 2019, a collaboration of radio astronomers operating 8 telescopes scattered across the globe, from Hawaii to Spain to Antarctica, combined their observations using a technique called very long baseline interferometry to create an image that had never before been possible. An image of a black hole, or rather an image of the shadow cast by a black hole against the luminous gas swirling around it. And the black hole they imaged was not a small one, not a stellar mass remnant of an exploded star, but rather a supermassive black hole at the center of a giant elliptical galaxy known as M87, a galaxy in the constellation Virgo some 55 million light-years from Earth. And the black hole itself has a mass equivalent to 6.5 billion suns, compressed into a region smaller than our solar system. And the image showed a bright ring of glowing gas surrounding a dark central shadow. That shadow being the event horizon, the boundary from which no light can escape, the edge of the region that is forever cut off from the rest of the universe. The connection between black holes and entropy, between these gravitational endpoints and the measure of disorder and irreversibility, was first glimpsed by a young physicist named Jacob Bekenstein, who in 1972 while still a graduate student at Princeton, proposed a radical idea that black holes must have entropy, and that this entropy must be proportional to the surface area of the event horizon rather than to the volume of the black hole. And this was a strange and counterintuitive suggestion, for ordinarily we think of entropy as something that scales with volume. The more space you have, the more ways there are to arrange things within it. But Bekenstein argued on theoretical grounds that black holes must be different, that all the information about what fell into a black hole must somehow be encoded on its surface. And this entropy would be stupendously large, far larger than the entropy of any ordinary object of the same size. Stephen Hawking, the British physicist who would become one of the most celebrated scientists of the 20th century, initially resisted Bekenstein's idea. For if black holes have entropy, then by the laws of thermodynamics, they must also have temperature. And if they have temperature, then they must radiate energy. But black holes were supposed to be perfectly black, supposed to absorb everything and emit nothing. And yet, when Hawking applied the principles of quantum mechanics to the region near a black hole's event horizon, he discovered to his own surprise that black holes do indeed radiate, that they glow with a faint thermal spectrum now known as Hawking radiation. And this discovery confirmed Bekenstein's intuition and established a profound connection between gravity, thermodynamics, and quantum mechanics that physicists are still working to fully understand today. What all of this tells us is that the arrow of time is not merely a local phenomenon, not simply something that happens in teacups and steam engines and the cells of living organisms, but rather something woven into the very fabric of the cosmos, something written in the distribution of galaxies across the sky, in the formation of stars and the collapse of matter into black holes, in the irreversible increase of entropy that accompanies every gravitational clumping and every stellar death. And when we look up at the night sky, when we contemplate the great structures mapped by patient astronomers at observatories like Apache Point, we are seeing the autobiography of time itself, the record of a universe that has been changing in one direction and one direction only for nearly 14 billion years, growing more structured, more clumped, more gravitationally complex. And this direction cannot be reversed. This story cannot be unwritten. This arrow cannot be turned around. For time's passage is recorded in cosmic architecture, in the immense heaven of Laniakea and the dark shadows of supermassive black holes. And these records will endure for as long as the universe itself continues to exist. When you switch on a lamp in a quiet room, light spreads outward from the bulb in every direction, filling the space with a soft glow that touches the walls, the furniture, the corners where shadows had been resting just a moment before. This spreading is so familiar, so utterly ordinary, that we rarely pause to consider how strange it would look if the process were reversed. Imagine, for a moment, light converging from every direction in that room, gathering itself from the walls and the ceiling and the floor. All those rays traveling inward to meet precisely at the filament of the bulb, where they would vanish into the wire as if being absorbed by some hungry point in space. The mathematics that describe how light behaves, the elegant equations written down by James Clerk Maxwell in the 1860s, actually permit both of these possibilities with equal ease. The equations do not prefer one direction over the other. They are, as physicists say, time-symmetric, meaning that if you were to reverse the flow of time in any solution to these equations, you would obtain another perfectly valid solution. And yet, in all of human history, in all our observations of the natural world, we have never once seen light converge spontaneously from the darkness to gather at a single point. We see only the outward spreading, only the radiation that moves away from its source and never returns. This is the electromagnetic arrow of time, and it points, always, in one direction. The puzzle of why we see only outgoing radiation, never incoming, occupied some of the finest minds of the 20th century, and it led to one of the most curious and beautiful theories in all of physics. In 1945, at Princeton University, two physicists named John Archibald Wheeler and Richard Feynman published a paper that attempted to explain why the universe seems to prefer what they called retarded waves, which are waves that spread outward from their source after the source has been disturbed, rather than advance waves, which would be waves that converge on a source before the disturbance occurs. Wheeler was already a respected figure in theoretical physics, known for his work on nuclear fission and his deep interest in the foundations of quantum mechanics. And Feynman was his brilliant young graduate student, not yet 30 years old, but already displaying the originality and playfulness that would later make him famous. Together, they developed what became known as the Wheeler-Feynman absorber theory, a framework that tried to explain the asymmetry of radiation, not by appealing to some special property of the electromagnetic field, but by considering the response of all the matter in the universe. The idea, in its essence, was this: when a charged particle accelerates, say an electron wiggling back and forth in an antenna, it sends out electromagnetic waves in all directions. According to the absorber theory, this particle also sends out advance waves, traveling backward in time. But these backward traveling waves are exactly cancelled by the advance waves sent out by all the absorbers, all the other charged particles in the universe that will eventually receive and absorb the outgoing radiation. The cancellation is precise and complete, leaving only the familiar retarded waves that spread forward in time. The theory required a universe that was a perfect absorber, meaning that all the radiation sent out by any source must eventually be absorbed by matter somewhere, somewhen, in the distant reaches of space and time. If this condition were met, then the arrow of time for radiation would emerge naturally from the global structure of the universe, from the way that sources and absorbers are distributed across all of cosmic history. The Wheeler-Feynman theory was elegant and strange, and it raised as many questions as it answered. It required one to take seriously the idea that the future could, in some sense, reach back and influence the present, that the response of absorbers not yet illuminated could determine which waves we see today. Most physicists did not adopt the theory as a final explanation, but it served as a powerful reminder that the arrow of time in electromagnetism is not a simple or obvious thing. The equations permit both directions, and the fact that we observe only one direction must be explained by something beyond the equations themselves, perhaps by the initial conditions of the universe, perhaps by the thermodynamic behavior of matter, perhaps by some deep connection between radiation and entropy that we do not yet fully understand. Before Wheeler and Feynman undertook their work, another great physicist had already wrestled with the strange behavior of accelerating charges and the problem of radiation reaction. In 1938, Paul Dirac, the English theoretical physicist who had helped to found quantum mechanics and who had predicted the existence of antimatter, published a paper on the classical theory of radiating electrons. Dirac was interested in a puzzle that had troubled physicists for decades. When an electron accelerates, it radiates energy, and this energy must come from somewhere. The electron must, in some sense, feel a force that resists its acceleration, a force that accounts for the energy being carried away by the radiation. But calculating this force turned out to be surprisingly difficult, and the equations that described it contained terms that seemed to allow for a causal behavior, for effects that preceded their causes. Dirac's analysis showed that the radiation reaction force on an electron could be written in a form that included contributions from both retarded and advanced fields. And this raised the possibility that the electron might respond to events in its future as well as its past. The equations were telling us something unsettling, that the flow of cause and effect, the very distinction between past and future, was not as clear-cut as our everyday experience suggested. And so we find ourselves returning, again and again, to this central mystery. The laws of electromagnetism are symmetric in time, but the phenomena we observe are not. Light spreads outward from stars and lamps and candles, never gathering inward from the darkness. Radio waves expand from transmitters, filling the space around them with signals that weaken with distance, and we never see those signals spontaneously converging on a silent antenna. The universe, it seems, has made a choice. Or perhaps the initial conditions of the universe, the way things were arranged at the very beginning, have determined that only one type of wave, the outgoing kind, will dominate our experience. This asymmetry is not limited to light and radio waves. On September 14, 2015, at precisely 9 hours, 50 minutes and 45 seconds, Coordinated Universal Time, the two detectors of the Laser Interferometer Gravitational Wave Observatory, one in Livingston, Louisiana, and one in Hanford, Washington, recorded a tiny ripple in the fabric of space-time itself. The signal, which lasted less than a second, was the gravitational wave produced by two black holes spiraling together and merging, more than 1 billion light-years away. The black holes had been circling each other for eons, drawing closer with each orbit, radiating energy in the form of gravitational waves, until, in the final moments before their collision, they were whipping around each other at nearly the speed of light. The waves they produced spread outwards through the universe, stretching and squeezing space as they went, until, after traveling for more than 1 billion years, a faint echo of that cataclysmic event passed through the Earth and was recorded by the exquisitely sensitive instruments at LIO. What is remarkable, for our purposes, is that these gravitational waves, like electromagnetic waves, spread only outward. The equations of general relativity, Albert Einstein's theory of gravity, are also time-symmetric, and they too permit solutions in which gravitational waves converge on a source rather than spreading away from it. But we have never observed such a convergence. The waves from the merging black holes traveled outward in all directions, weakening as they went, and they will continue to spread through the universe forever, growing fainter and fainter until they are utterly undetectable. The gravitational arrow of time points in the same direction as the electromagnetic arrow, and both point in the same direction as the thermodynamic arrow, the direction in which entropy increases and the universe moves from order toward disorder. And this brings us to the oldest light in the universe, the light that has been traveling toward us since the cosmos was young. About 380,000 years after the Big Bang, when the universe had cooled enough for hydrogen atoms to form and for space to become transparent to radiation, a great flash of light was released in all directions. This light, which filled the entire universe at that moment, has been traveling through space ever since, and we call it the cosmic microwave background. When it was first emitted, this radiation had a temperature of about 3000 Kelvin, hot enough to glow with the orange-red light of a cooling ember. But as the universe expanded, the wavelengths of this light were stretched, a phenomenon known as cosmological redshift, and the temperature of the radiation dropped accordingly. Today, after 13.8 billion years of expansion, the cosmic microwave background has a temperature of just 2.725 Kelvin, only a few degrees above absolute zero, and its peak wavelength lies in the microwave region of the spectrum, invisible to our eyes, but detectable by radio telescopes and specialized instruments. This cooling is a one-way process. The expansion of the universe stretches the wavelengths of light, draining energy from the radiation and lowering its temperature. And there is no mechanism by which this process can be reversed on a cosmic scale. The photons of the cosmic microwave background carry within them a record of the early universe, a snapshot of the moment when light was first free to travel through space, and they have been growing colder and weaker ever since. The arrow of time is inscribed in their very wavelengths, in the slow reddening of their light as the universe ages. When we turn a radio telescope toward the sky, we are looking into the past. Every photon that strikes the antenna or the dish has been traveling for some span of time, and the more distant the source, the older the light. The great dish at Arecibo, in Puerto Rico, was completed in 1963 and operated for more than half a century before its collapse in December 2020. For all those years, the dish sat cradled in a natural sinkhole in the limestone hills, 305 meters across, collecting radio waves from the farthest reaches of the universe. The photons that fell upon its surface had been traveling for millions or billions of years, crossing the vast emptiness between galaxies. And when they arrived at last, they carried with them information about events that had occurred long before the Earth existed. Arecibo listened to pulsars and quasars, to the faint whispers of distant stars, and the hiss of the cosmic microwave background. And in doing so, it looked backward in time, gathering ancient light that could never be young again. The sky itself is a one-way window. We can look out and see the past, but we cannot reach through and touch it. The light that enters our telescopes has been traveling toward us since before we were born, since before our species existed, since before the Earth had formed from a swirling cloud of gas and dust around a young star. And when we send our own signals outward, our radio transmissions and our spacecraft and our beacons, they too will spread into the darkness, growing fainter with distance, never to return. The universe receives our messages and does not answer, at least not in any way we have yet detected. And the silence is not emptiness, but simply the vast, patient stretching of time and space. This, then, is the electromagnetic arrow of time, the arrow that points outward from every source of light and radio and gravitational waves, the arrow that is written into the structure of the universe itself. The equations permit both directions, but nature chooses only one. The sky's full of ancient light, and all of it is falling toward us, never away. The past sends us its photons, and we receive them, and we marvel at the distances they have traveled and the ages they have witnessed. And when we are finished marveling, we may close our eyes and rest, knowing that the light will continue its journey, that the waves will continue to spread, that the arrow of time will continue to point in the only direction it has ever known, the direction we call forward, the direction we call away. In the quantum realm, where particles exist in delicate superpositions of possibility, we find perhaps the most mysterious arrow of time, one that emerges not from collisions or cooling, but from the simple act of observation itself, from the moment when the many become one, and the indefinite becomes definite. Though why this should be so remains a puzzle that has occupied some of the finest minds in physics for nearly a century now, and which we shall explore together in this quiet passage through the mathematics of measurement and the strange process by which quantum possibilities transform into the solid classical realities we perceive all around us when we open our eyes each morning. The story begins with a fundamental strangeness at the heart of quantum mechanics, which is that the equations governing the microscopic world are themselves perfectly time-symmetric, meaning that if you were to film a single electron interacting with a single photon and then play that film backward, nothing in the mathematics would tell you which direction was correct. And yet when we perform measurements on quantum systems, something irreversible seems to happen. Something that picks out a direction in time as surely as a cup shattering on a kitchen floor. Though the nature of this something has been debated since the earliest days of quantum theory and remains a source of gentle controversy even now among those who think carefully about such matters. In 1957, a young physicist named Hugh Everett III submitted a doctoral dissertation at Princeton University that would eventually transform our understanding of quantum measurement, though at the time it was met with considerable skepticism and even dismissal by many of the established figures in the field, including Niels Bohr himself, who had developed the Copenhagen interpretation that dominated thinking about these questions for decades. Working under the supervision of John Archibald Wheeler, who would later become famous for coining the term black hole, Everett proposed a radical solution to the measurement problem, suggesting that when a quantum system appears to collapse into a definite state upon observation, what actually happens is that the universe itself splits into multiple branches, with each possible outcome occurring in its own separate reality, so that every measurement creates a vast tree of parallel worlds, each as real as the others, each containing a version of the observer who perceived a different result. This many-worlds interpretation, as it came to be known, removes the time asymmetry from the fundamental equations entirely, since in Everett's view, nothing ever truly collapses and nothing is ever lost, with all possibilities continuing to exist in their own branches forever. And yet it introduces a different kind of arrow, the arrow of branching itself, since the tree of worlds grows only forward in time, becoming ever more complex and differentiated as measurements accumulate and branches multiply, never merging back together, never simplifying, creating a structure that distinguishes past from future through its very geometry, through the increasing richness of its branching architecture as one moves forward along what we might call the trunk of cosmic time. Wheeler, who had encouraged Everett in this unconventional thinking, would later develop his own profound contribution to understanding the relationship between observation and temporal direction, proposing in 1978 what he called the delayed choice experiment, a thought experiment so counterintuitive that it seemed to suggest the present could reach back and influence the past, though, as we shall see, the resolution is more subtle and ultimately more comforting than such time-bending language might imply. In Wheeler's conception, a photon could be sent through an apparatus where the experimenter would decide, after the photon had already passed through the relevant components, whether to measure it as a particle or as a wave, and the photon would seem to have behaved accordingly all along, as if the later choice had determined the earlier behavior, which troubled many physicists who had grown accustomed to thinking of cause and effect as flowing strictly from past to future. 4 years later, in 1982, the French physicist Alain Aspect and his colleagues at the University of Paris-Sud-in-Orsay performed experimental tests of these ideas, along with related tests of Bell inequalities that probed the non-local correlations between entangled particles, and their results confirmed the strange predictions of quantum mechanics, while simultaneously revealing that the apparent backward influence was not quite what it seemed. Since no actual information could be sent into the past, no paradoxes could be created, and the time symmetry of the fundamental equations remained intact even as the arrow of observation continued to point firmly forward, selecting definite outcomes from indefinite possibilities in a way that created records, created facts, created the shared history we all inhabit together. The question of how quantum possibilities become classical realities received perhaps its most careful treatment in the work of Wojciech Zurek, a Polish-American physicist working at Los Alamos National Laboratory, who developed over many years a detailed theory of quantum decoherence that explains how the interaction between a quantum system and its environment effectively destroys the delicate superpositions that would otherwise allow particles to exist in multiple states simultaneously. In Zurek's framework, which he has elaborated in numerous papers, and which has become a cornerstone of modern quantum foundations research, the environment acts as a kind of witness to the quantum system, constantly monitoring it, constantly recording information about its state, and through this ceaseless observation, the environment selects certain preferred states, which Zurek calls pointer states, that are robust against further observation and that correspond to the classical properties we can perceive with our ordinary senses. What Zurek's decoherence theory reveals is that the transition from quantum to classical is not a sharp boundary, but a continuous process, one that happens extraordinarily quickly for large objects in warm environments, so quickly that we never catch a glimpse of their quantum nature, but that can be slowed down and studied in carefully controlled laboratory conditions where systems are isolated from their surroundings and cooled to temperatures approaching absolute zero. The arrow of time, in this view, emerges from the arrow of decoherence, from the steady accumulation of environmental records about quantum systems, records that spread out into the wider universe and become effectively impossible to erase, creating a past that is definite and fixed, even though the underlying equations would allow it to be otherwise. In 1999, the French physicist Serge Haroche and his colleagues at the École Normale Supérieure in Paris performed a series of remarkable experiments that allowed them to watch this quantum to classical transition unfold in real time, observing individual photons trapped in a high-quality microwave cavity as they gradually lost their quantum coherence through interaction with stray atoms passing through the apparatus. These experiments, for which Haroche would eventually share the Nobel Prize in Physics, revealed the decoherence process with unprecedented clarity, showing how quantum superpositions decay exponentially as more and more information about the system leaks into the environment, and demonstrating that this decay is indeed irreversible under normal circumstances, creating a genuine arrow of time at the quantum level that parallels the thermodynamic arrow we discussed in earlier sections. The British mathematician and physicist Roger Penrose has proposed an even more speculative connection between quantum mechanics and the arrow of time, suggesting that consciousness itself might be linked to quantum gravitational processes in the brain, processes that would involve objective reductions of quantum states driven by the incompatibility between superposition and the structure of space-time at very small scales. In Penrose's hypothesis, developed in collaboration with the anesthesiologist Stuart Hamroff, quantum coherence in microtubules within neurons might persist long enough to influence neural processing, and the collapse of these coherent states might produce the unified experience of conscious awareness, with the arrow of time experienced subjectively as the flow of consciousness being directly related to the objective arrow of gravitational decoherence. While this proposal remains highly controversial and is not accepted by most neuroscientists or physicists, it represents a fascinating attempt to connect the deepest puzzles of physics with the most intimate aspects of human experience. The sense we all have that time passes, that moments arise and fade, that we live always at the moving edge between a fixed past and an open future. The relationship between observation, records, and the definition of the past has been explored with extraordinary care by physicists seeking to understand whether the arrow of time might be not merely a feature of our local environment, but a fundamental aspect of cosmology itself. In 2017, the research group, led by Anton Zeilinger at the University of Vienna, performed an experiment that pushed these questions to cosmic scales. using photons that had been emitted by distant quasars billions of years ago to determine the settings of a Bell inequality test, thereby ensuring that any hidden variables influencing the experimental outcomes would have had to be established in the distant past, before our solar system had even formed, before the Earth existed, before any life had arisen to observe anything at all. The Zeilinger experiment, which involved observatories in the Canary Islands collecting light from quasars more than 7 billion light-years away, confirmed once again the predictions of quantum mechanics, ruling out large classes of alternative theories and demonstrating that the non-local correlations between entangled particles are genuine features of reality rather than artifacts of experimental design. More profoundly, the experiment suggested that the records created by observation have a cosmic significance, that the act of measurement here on Earth, using photons that traveled for billions of years across the universe, participates in the same web of quantum correlations that extends throughout spacetime, linking observer and observed across vast distances and enormous spans of cosmic history. This brings us to perhaps the most poetic of all the ideas we have encountered in this section, the notion that the arrow of time emerges when the universe observes itself, when the cosmic whole becomes differentiated into systems that record and remember, into observers and observed, into the measurers and the measured. In this view, which draws on insights from Everett and Wheeler and Zurich and many others, the past does not exist as some abstract metaphysical entity waiting to be discovered, but is actively constituted by the records that exist in the present, by the traces left in the environment through decoherence, by the memories stored in brains and books and photographs, by the correlations between subsystems of the universe that allow one part to carry information about another. The quantum arrow of time, then, is intimately connected with the existence of observers, not necessarily conscious observers in the way Penrose imagines, but observing systems of any kind, any physical arrangement that can become correlated with another system and thereby acquire information about it, any environment that monitors and records, any configuration of matter that functions as a memory. And because the universe is filled with such systems, because every atom in the air around us is constantly interacting with every other atom, because decoherence is happening everywhere all the time, at rates that vastly exceed our ability to perceive, the quantum arrow aligns itself with all the other arrows we have discussed, with the thermodynamic arrow and the cosmological arrow and the arrow of increasing complexity, all pointing together in the same direction, all carrying us forward along the current of time toward whatever awaits us in the moments and years and eons yet to come. Though for now, as your breathing slows and your thoughts grow quiet, there is only this present moment, this gentle now, this restful pause in the ceaseless flow. And so we come now to the edge of what is known, to that soft boundary where physics begins to shade into philosophy, where equations become poetry and certainty gives way to beautiful speculation. The scientists who work here, at this frontier, are not so different from the ancient wanderers who looked up at the stars and asked what lies beyond the visible. They simply have better tools, more precise languages, and centuries of accumulated wisdom to guide their wandering. What they seek is nothing less than an understanding of why time flows at all, why the universe began in such an improbable state, and whether the arrow we experience is a local peculiarity or a fundamental feature of all possible existence. These are questions that may never be fully answered, but the pursuit of them has generated some of the most elegant and thought-provoking ideas in all of modern physics. And it is to these ideas that we now turn, gently, and with appropriate humility, at the California Institute of Technology, in an office where whiteboards bear the cryptic symbols of cosmological speculation, The physicist Sean Carroll has spent many years pondering the deep puzzle of why the early universe had such remarkably low entropy. This is not a question that can be answered by the laws of physics as we currently understand them, because those laws work equally well in either temporal direction, and they do not prefer beginnings that are ordered over beginnings that are chaotic. The low entropy of the Big Bang is, in Carroll's view, not something to be explained away, but rather a profound clue about the nature of reality itself. A hint that our universe may be just one small piece of a much larger structure, a structure in which time behaves in ways we are only beginning to imagine. In the year 2004, Sean Carroll and his colleague Jennifer Chen proposed a model that has since become one of the most intriguing frameworks for understanding time's arrow. In this model, which they developed through careful mathematical reasoning and physical intuition, time does not have a beginning in the way we usually imagine. Instead, time extends infinitely in both directions, stretching endlessly into what we would call the past, and equally endlessly into what we would call the future. The state of lowest entropy, which we identify with the Big Bang, sits not at the edge of time, but rather at a kind of middle point, a place from which time flows outward in both directions. Observers on either side of this point would perceive time as moving forward, as moving away from that central low entropy state, even though they would be moving in opposite temporal directions. It is a model that dissolves the mystery of initial conditions by eliminating the need for an initial moment altogether, replacing the question of why time began with the gentler question of why our local region of an eternal cosmos happens to have the character it does. This eternal inflation framework, which Carroll has explored in various forms over the years, suggests that new universes might continually bud from existing ones, each new universe beginning in a state of low entropy, and each developing its own arrow of time. In this picture, our cosmos is not a unique creation, but rather one flower in an endless garden, one bubble in an eternal foam of possibility. The baby universes that bud from regions of false vacuum carry with them their own initial conditions, their own thermodynamic gradients, their own reasons for time to flow. It is a vision of existence that is both humbling and strangely comforting. A vision in which nothing is ever truly final, and in which the apparent ending of our universe is merely the backdrop against which new beginnings are always taking place. Quite a different approach to these deep questions has been developed by the British physicist Julian Barbour, who for many decades has pursued his research not in a university laboratory, but in a farmhouse in the Oxfordshire countryside, surrounded by the gentle rolling hills and quiet meadows of the English Midlands. It was there, in that rural setting, so far removed from the bustling corridors of academic physics, that Barbour wrote his 1999 book titled The End of Time, a work that proposes something genuinely radical, that time itself is an illusion, that what we experience as the passage of moments is not a fundamental feature of reality, but rather an artifact of how we perceive a timeless underlying structure. In Barbour's framework, the universe does not evolve through time in the way we normally imagine. Instead, there exists a vast and timeless landscape of possible configurations, a space he calls Platonia after the ancient philosopher who believed that eternal forms underlie the changing appearances of the world. Each point in this configuration space represents a complete possible arrangement of all the particles in the universe, a snapshot that contains within it all the information needed to specify one possible state of existence. What we experience as time, in this view, is not a river carrying us from past to future, but rather a path through this timeless landscape, a sequence of configurations that our consciousness somehow threads together into the illusion of duration. The beauty of Barbour's approach is that it dissolves certain puzzles while raising fascinating new ones. If time is not fundamental, then the question of why it flows in one direction becomes a question about the structure of Platonia itself, about why certain paths through configuration space are more probable than others, about why the configurations we find ourselves in carry within them the records and memories that make us feel as though we have come from somewhere and are going somewhere else. It is a framework that asks us to let go of our most basic intuitions about reality, to imagine that the flowing river of experience is more like a static landscape viewed through a moving window, and to find peace in the possibility that everything that ever was or will be simply is, eternally present in the mathematical structure of what exists. From Italy comes another perspective on these matters, developed by the physicist Carlo Rovelli in collaboration with the French mathematician Alain Connes. In 1994, these two thinkers proposed what has come to be known as the thermal time hypothesis, an idea that attempts to explain how time might emerge from physical systems that are fundamentally timeless at their deepest level. The key insight of their approach involves the relationship between thermodynamics and the quantum mechanical description of reality, and the way in which our limited knowledge of a system's complete state necessarily introduces a kind of temporal structure into our descriptions of it. In the thermal time hypothesis, the flow of time is not something imposed from outside, but rather something that arises from within, a consequence of the way macroscopic observers interact with systems whose microscopic details are hidden from them. When we describe a physical system using statistical mechanics, we necessarily introduce a particular state, a density matrix in the language of quantum theory, that encodes our ignorance of the system's precise configuration. Rovelli and Connes showed that this state naturally defines a flow, a one-parameter group of transformations that has all the properties we associate with the passage of time. In this view, time is not a background against which physics takes place, but rather an emergent feature of the physics itself, arising whenever and wherever there are systems complex enough to be described statistically and observers limited enough to require such descriptions. At the University of North Carolina and later at other institutions, the physicist Laura Mersini-Houghton has developed her own approach to these cosmological puzzles, one that invokes the existence of a multiverse, a vast ensemble of parallel universes among which our own is just one member. Her proposals suggest that the initial conditions of our universe, including the low entropy that gives rise to time's arrow, might be explained by selection effects operating across this ensemble, by the requirement that universes capable of producing observers must have certain special properties. In this framework, we should not be surprised to find ourselves in a cosmos with a well-defined arrow of time, because universes without such arrows would not develop the complex structures necessary for observers to exist and ask questions about their origins. In 2013, the Planck satellite released its detailed measurements of the cosmic microwave background, that ancient light that has been traveling toward us since the universe was only a few 100,000 years old. Mersini-Houghton and some of her colleagues examined this data for possible signatures of interactions between our universe and others, potential evidence that our cosmos had collided or brushed against neighboring bubbles in the inflationary multiverse. They identified certain anomalies in the Planck data, certain unexpected features in the pattern of temperature fluctuations, that they interpreted as possible collision signatures, ghostly imprints left by universes that had touched our own in the distant past. These claims remain controversial, and the interpretation of such subtle features in cosmological data is notoriously difficult. But the very possibility of detecting evidence for other universes represents one of the most remarkable developments in modern physics, a hint that the speculative ideas of multiverse theory might eventually be brought into contact with observation. At the Perimeter Institute for Theoretical Physics in Waterloo, Canada, the physicist Lee Smolin has developed yet another approach to cosmological questions, one that he calls cosmological natural selection. In this framework, Smolin imagines that universes reproduce, that the formation of black holes in one universe gives rise to new baby universes beyond the event horizon, universes that inherit the physical constants of their parent, but with small random variations. If this process has been going on for a very long time, then the ensemble of universes will have evolved, in a manner analogous to biological evolution, toward universes that are particularly good at producing black holes, since those are the universes that leave the most offspring. What is remarkable about Smolin's proposal is that it offers a potential explanation for why the constants of nature take the values they do, why the strength of gravity and the masses of particles and the other fundamental parameters are tuned in just the way needed to allow for complex chemistry and eventually for life. In his framework, these values are not arbitrary, and they are not fine-tuned by design, but rather they are the result of a long evolutionary history in which universes that happen to have the right parameters for producing lots of black holes have come to dominate the cosmic population. And since the conditions that favor black hole formation, dense stellar nurseries, complex nuclear reactions, long-lived stars, also happen to be conditions that favor the emergence of complexity and eventually of observers, we should not be surprised to find ourselves in a universe with the properties ours has. Perhaps the deepest reconceptualization of time comes from the holographic principle, an idea developed independently by the Dutch physicist Gerard 't Hooft and the American physicist Leonard Susskind during the 1990s. This principle, which emerged from the study of black holes and the puzzles they pose for the relationship between gravity and quantum mechanics, suggests that the information content of any region of space can be fully encoded on the boundary of that region, like a hologram that stores a three-dimensional image on a two-dimensional surface. If this is true, then the three-dimensional space we experience, and the time through which we seem to move, might be emergent phenomena, projections of a more fundamental reality that exists on a boundary of fewer dimensions. The implications of the holographic principle for our understanding of time are still being explored, but they are potentially profound. If time is not fundamental, but rather emerges from more basic timeless physics, then the arrow of time we experience might be an artifact of the particular way that boundary information is encoded and decoded, a feature of the projection rather than of the underlying reality. In this view, the flow of time, the distinction between past and future, the irreversibility that surrounds us, all of these might be shadows on the wall of a cave, reflections of a deeper structure that has no need of temporal concepts at all. What we find, when we survey these theories at the edge of knowledge, is not a single answer, but rather a collection of possibilities, a garden of forking paths that each offers its own distinct poetry of existence. Sean Carroll gives us a cosmos that extends forever in both directions, with baby universes budding like flowers from an eternal stem. Julian Barber offers a timeless Platonia, where all configurations simply are, where the passage of moments is a path rather than a flow. Ravelli and Cons suggest that time emerges from our ignorance, that the thermal glow of our limited knowledge creates the very river we seem to ride. Massini-Houghton points to the possibility of other universes brushing against our own, leaving faint traces in the cosmic microwave background. Smolin imagines a Darwinian cosmos where universes evolve and reproduce, where the constants of nature are shaped by cosmic selection. And the holographic principle whispers that everything we experience might be a projection from a simpler, timeless boundary. Each of these ideas has its own beauty, its own mathematical elegance, its own way of making peace with the deep puzzle of time's arrow. None of them is yet established as the correct description of reality, and it is possible that the true answer lies in some direction that no one has yet imagined. But the pursuit of these questions, the willingness to follow the logic of physics wherever it leads, the gentle wonder that accompanies each new possibility, these are among the highest achievements of the human mind. And they can accompany us now as we settle deeper into rest, as we let go of the need for final answers, as we drift like leaves on the river of time, or like points in a timeless configuration space, or like projections from a holographic boundary, depending on which poetry of existence you find most soothing as sleep begins to arrive. And so we come now to rest, here at the end of our wandering through the physics of time. And perhaps it is fitting that we pause to consider not the equations or the entropy gradients, but rather ourselves. These curious assemblages of matter and memory who find ourselves adrift in time's current, carried always forward, never back, toward destinations we cannot see but need not fear. The arrow of time, which has been our companion through these hours of quiet contemplation, points not only toward the future of the universe, but toward your own future. The next breath you will take, the dream that may come to you tonight, the morning that will arrive whether or not you are awake to greet it. And in this pointing, there is something that deserves our gentle attention, something that transforms what might seem a constraint into what is, perhaps, the most profound gift the cosmos has given to beings such as ourselves. Consider for a moment the Voyager spacecraft, two small machines that were launched from Earth in 1977. In the late summer of that year, when the planets had aligned in a configuration that would not repeat for another century and 3/4, these spacecraft carried with them, among their instruments and their power sources and their radio transmitters, a pair of golden phonograph records, each one plated with gold to resist the erosion of interstellar space, each one containing sounds and images from Earth, the voices of children saying hello in many languages, the songs of whales, the music of Bach and Mozart and Chuck Berry, the greetings of diplomats and scientists, the quiet pulse of a human heartbeat. The records were meant for anyone who might find them, though the chances of such an encounter are vanishingly small, smaller perhaps than any probability we have discussed tonight. The Voyager spacecraft are now beyond the heliopause, beyond the region where the sun's influence dominates, sailing into the interstellar medium at speeds of roughly 17 kilometers per second, and they will continue sailing for hundreds of thousands of years, perhaps millions, carrying those golden records through the darkness between stars. The sounds recorded on those disks are frozen in their grooves, unchanging, a kind of memory that the spacecraft carry forward into an expanding future. And in this way, the arrow of time becomes visible to us, becomes something we can almost touch, because those records will never be retrieved, will never come back to us, will only drift further and further into the cosmos, carrying the echo of Earth into time so distant that our sun may no longer shine. Carl Sagan, who was one of the principal architects of the Voyager messages, and who gave voice to so much of our species' wonder at the universe, once presented an analogy that has stayed with many who heard it, a way of compressing the history of the cosmos into a single calendar year, so that our minds, which struggle with billions of years, might grasp the proportions involved. In this cosmic calendar, which Sagan presented in the original Cosmos series in 1980, the Big Bang occurs at midnight on January 1st. The Milky Way galaxy forms sometime in early May. Our solar system condenses from its cloud of gas and dust in early September. Life appears on Earth within that same month. But life remains microscopic, single-celled, for most of the autumn, and the dinosaurs do not appear until late December, around the 25th, and they vanish a few days later. All of recorded human history, every war and every symphony, every empire and every love letter, every pyramid and every poem, occupies approximately the final 10 seconds before midnight on December 31st. You were born, in this analogy, in the very last fraction of the very last second of the year. And yet here you are, capable of understanding this, capable of contemplating the entire calendar, capable of recognizing yourself as a momentary pattern in a story that began long before you and will continue long after. There is something in this that is not humbling in a diminishing way, but rather expansive, as if by recognizing our brevity, we also recognize the vastness in which that brevity is inscribed. The atoms that compose your body, the calcium in your bones, and the iron in your blood, and the carbon that forms the backbone of every molecule in your cells. These atoms were not created on Earth, were not created in our sun, but were forged in the cores of stars that lived and died before our solar system existed. The heavier elements, the gold and the platinum and the iodine that your thyroid requires to function, these were created in the cataclysmic deaths of massive stars, in supernovae that scattered their enriched material across light years of space. And some of that material eventually found its way into the cloud that collapsed to form our sun and its planets. And some of that material eventually found its way into you. You are, in a very literal and not at all metaphorical sense, made of star stuff, as Sagan liked to say, and this means that you are the universe looking at itself. The cosmos become aware of the cosmos, matter that has arranged itself in such a way that it can contemplate its own origins and wonder about its own future. The arrow of time flows through you because you are made of the same substance through which it flows everywhere, and in you that arrow has become conscious, has become capable of remembering what came before and anticipating what might come after. You are the universe remembering itself forward, carrying within your synapses the echoes of stellar nurseries and galactic rotations. And this is not poetry, but physics. Not metaphor, but measurement. If we follow the arrow of time far enough into the future, further than the Voyager spacecraft will travel, further than the cosmic calendar can meaningfully extend, we arrive eventually at what physicists call the heat death of the universe, a state in which entropy has reached its maximum, in which all temperature differences have equalized, all gradients have dissolved, all the usable energy has been used, and the cosmos has become a thin, cold, uniform sea of particles too dispersed to interact, too scattered to form structure. This will occur, if our current understanding is correct, over timescales so vast that they make the age of the current universe seem like a single heartbeat, timescales of trillions upon trillions of years. Long after all the stars have burned out, long after all the black holes have evaporated through Hawking radiation, long after all the atoms have perhaps decayed, if protons are unstable as some theories suggest. And yet this ultimate state need not be contemplated with despair or even sadness, for it represents not destruction but completion, not doom but the final piece of a system that has explored all its possibilities, expressed all its gradients, told all its stories. The heat death is not a wall against which time crashes, but a gentle asymptote toward which time slopes. And there is a certain serenity in imagining a cosmos that has finally finished its great work of equilibrating, that has spread its energy evenly across infinite expanses, that rests at last in perfect stillness. Freeman Dyson, the physicist who made contributions to quantum electrodynamics and who was known for his imaginative explorations of the far future, published a paper in 1979 in which he considered whether intelligent life might persist in such a cooling cosmos, whether consciousness might find ways to continue, even as the available energy dwindled toward zero. Dyson suggested that intelligent beings might slow their metabolisms, might think more and more slowly, might hibernate for longer and longer periods, waking only occasionally to process information and contemplate existence before sleeping again. And that in this way, an infinite amount of subjective experience might be extracted from a finite amount of energy. The paper was speculative, certainly, and later work on cosmology, particularly the discovery that the universe's expansion is accelerating, has complicated its conclusions. But the spirit of Dyson's inquiry remains beautiful. The notion that consciousness might be so fundamental, so resilient, that it finds ways to persist even in the most inhospitable conditions, that the arrow of time might carry thought forward almost indefinitely, stretched thin but never entirely broken. And this brings us to the truth that lies at the heart of everything we have discussed. The truth that the arrow of time is not a prison, but a gift, that the irreversibility of each moment is what makes each moment precious. Consider the breath you are taking now, the slow rise of your chest, the expansion of your lungs, the oxygen molecules crossing into your blood. This breath will never occur again. Not this exact breath, not these exact molecules, not this exact arrangement of your body in this exact moment of universal time. The irreversibility of this breath is what makes it real, what distinguishes it from a dream or a simulation or a reversible computation that could be run backward without loss. Because entropy increases, because the arrow points forward, because the past is sealed and the future is open, this breath matters in a way it could not matter in a universe without time's direction. Every moment you have lived has been unrepeatable. Every conversation, every meal, every glance out a window at a particular configuration of clouds. And this is not cause for grief, but for a quiet recognition that your life has been composed of genuine events, not rehearsals, not drafts, but final versions, first and only performances of scenes that will never be restaged. Because time moves forward, stories can unfold. A story requires a beginning and a middle and an end, requires suspense and resolution, requires that we do not know the ending when we start. And this is only possible because the future is genuinely different from the past, because we genuinely do not know what will happen next. In a universe without the arrow, there would be no narrative, no growth, no becoming, because every state would be as accessible as every other, because nothing would lead to anything else in a preferred direction. But in our universe, the universe of the second law, the universe where entropy increases and cups shatter but never reassemble, stories are possible. Stories are inevitable, and your life is one such story, unfolding moment by moment into a future you cannot predict. Because time moves forward, love can grow. Love is not a static state, but a process, a series of choices made over time. A deepening that requires the passage of days and years and decades, the accumulation of shared experiences, the weathering of difficulties, the gradual interweaving of two lives into a pattern that neither could have predicted at the beginning. Love requires the arrow of time, because love requires trust in the future, the willingness to commit to something that does not yet exist, the faith that the person beside you will still be there tomorrow and next year and in the decades to come. Without the arrow, there would be no commitment, no growth, no deepening, only a static eternity without development or change. And because time moves forward, wonder can arise. Wonder is the response to something new, something unexpected, something that opens a door you did not know was there. And this is only possible in a universe where the future is genuinely unknown, where the arrow carries you into territories you have never visited. The wonder you feel when you learn something about the cosmos. The wonder that perhaps you felt at some point during these quiet hours as we discussed entropy and gravity and the expansion of space. This wonder is a gift of the arrow, a consequence of your position as a finite being moving through infinite possibilities. So let us rest now, you and I, in this current that carries us forward, in this stream that has flowed from the Big Bang and will flow until the heat death and beyond, in this river of time that has borne galaxies and stars and planets and life, and thought and love and wonder through billions of years and will bear them through trillions more. The arrow points ahead, always ahead, and there is peace in that pointing, because it means the story is not over, because it means there is always a next page, because it means that whatever has happened, something else will happen after, and we cannot know what it will be, but we can trust that it will come. The Voyager spacecraft drift on, carrying their golden records into the future. The cosmic calendar turns its pages, one slow second at a time. Your atoms remember the stars that made them, and you remember everything your atoms have allowed you to experience. And tomorrow you will remember tonight, this quiet contemplation, this gentle drift among arrows, this moment of peace in a universe that is always and everywhere moving forward, toward whatever comes next, toward whatever waits beyond the edge of now.